In the Middle Ages, the Mongolian horde under Genghis Khan brought the bubonic plague from Central Asia to Europe. In the year 1346, a Mongol and Tartar army besieged the Ukrainian city of Feodosia by using catapults to launch plague-ridden corpses over the fortress wall into the city. This was the beginning of the Black Death, and also an early instance of biological warfare. To pull it off, the Mongolian siege engineers had a projectile problem to solve. They had to launch their corpse over the wall. Suppose their catapult was able to adjust the angle at which it launched, but not the launch speed. You would have to then determine the appropriate angle to get the body over the wall. Let's say we're given the following information. We know how far the catapult can safely be from the wall, out of range of the archers and so forth on top of the wall. So we know this distance here, and we know the height that we need to get our projectile up to get it just over the wall. And we know the launch speed from the catapult. We don't know the angle we need to launch at, and we don't know how long it's going to take, the time to get to the top right there. In a situation like this, to solve for the angle, our strategy is as follows. We're going to, one more moment. If we don't know the angle here, then we also don't know the x component of our projectile's velocity or the y component of the initial velocity. But we can write that the x component can be written as v1 cos theta. We know the speed, we don't know the angle. And the y component of the initial velocity is v1 sine theta. So we'll be using these two facts. Okay, so now our strategy is to take these two equations from our set of projectile equations, and notice we've got two unknowns here. Vx contains the unknown theta, v1y contains the unknown theta, and we've also got the time is an unknown. What we want to do is eliminate time between these two equations to get an equation just in terms of the angle theta. So first we're going to replace Vx with this expression and V1y with this expression, giving us these. And then I'm going to solve for delta t right here and plug it in to this equation. So solving for delta t from this equation, I get this expression here, and this is going to be plugged in for delta t right there and for delta t right there. Here I've done so. It went in for delta t. Here this whole expression is squared. And now I'll simplify further. Here I've got speed over the speed. That cancels out. And we've seen this before. Sine theta over cosine theta. I use my trig identity to say that's equal to tangent theta. So sine over cosine becomes tangent theta, and I can rewrite this as delta y equals tangent of theta times delta x minus 1/2 g, and then this expression here. So there's our unknown theta, there's our unknown theta, but the rest of this information is known to us. We know delta y and delta x, we know the launch speed, we know delta x, and of course we know what g is. So we've got an equation in terms of theta here that can be solved by graphing. What you want to do is put this into your calculator and solve it by graphing. Let me recommend a method of doing that. I would subtract delta y from the left-hand side, put it on the right-hand side. So now you've got 0 equals this whole expression here. I would put this expression into your calculator, putting in numbers for all the givens here, putting numerical values for everything in green, and then leave theta there as your variable. Theta is your variable. Then we want to find where this expression equals 0. We want to find the values of theta that make this expression equal to 0. In other words, what we want to do is find the zeros of this function. So we want to graph this function and find at what values of theta does it equal 0. And of course, to be physically realistic, those theta values have to be between 0 and 90 degrees. So we're only looking at that part of our horizontal axis. Here's a concrete example. Let's say that these were your given pieces of information. If you put those values in here and graph this function and looked at the graph between 0 and 90 degrees, you would find that it intersected the x-axis twice. 2 zeros, therefore 2 solutions. That is 35.4 degrees right here, or 69.8 degrees. What that means is there are 2 possible angles you could launch at to get over the fortress wall. 35.4 degrees would launch you on this trajectory here, sort of skirting right over the top, or you go to a bigger angle, 69.8, that'll get you up high and then right down through that same point. Both these trajectories will take you through that point right there, get you inside the fortress. For more hilarious scenarios involving projectiles, catapults, and the plague, watch Monty Python and the Holy Grail.